So Brandon, I called this more friction examples because friction is a tricky force to wrap our brain around. And now we're going to be getting into more complicated free body diagrams and more complicated who's winning, who's losing situations. First situation, how many of you have ever pushed those wooden benches in the gym, the ones that sit there? How many of you have ever tried pushing those across the floor? Okay, so it says, example 1, consider the bench below, which is being pulled by student number 1. Oh heck, let's make it Ange. Across a rough surface at a constant speed. You know what? We should probably make a note that that's going to be important. Suddenly, student number 2 pushes down on the bench. You know what? Suddenly, Gershine comes along and sits on the bench because, you know, you've all seen kids do that one. So Ange is pushing or pulling, doesn't matter, this bench along at a constant speed. And then Gershine decides to sit on it. If Ange maintains the same force as before, what happens to A, the weight of the bench, B, the normal force of the bench, C, friction, and then D, the motion? Let's see if we can answer that. Now, I'm hoping you can imagine what happens. What I'm really saying is, can we explain the physics behind why everything happens? What might this be a good job for? Okay, I did the free body diagram for the first situation here, although I wasn't really careful. So we have F applied, and F applied and friction, are they bigger, smaller, or the same size? How do you know they have to be the same size? Constant speed. So I know these two arrows are the same. And is the bench sinking into the ground like quicksand? Is it flying through like Superman? So I know these two should be the same, and I had trouble getting, because it kind of looks now like the normal force is a bit longer. Really, you know what I should have done? I should have had that line go right to there. Now they're the same size-ish, close-ish. Okay. Let's look at now someone sitting on the bench. What are the forces acting on the bench? Get the obvious one. Has that changed from before? Gravity hasn't changed. I'll do it in red so you can see it a bit better. Is this bench sinking into the ground like quicksand? Is it flying into the air like Superman? What that means is vertically, the forces must be, I'm looking for where that starts, letter B, balanced. What that really means is everything down has to equal everything. Gravity. What force am I going to draw next? Normal force. Bigger, smaller, or the same size as gravity? This is the aha moment, so turn your brain on. Okay, it can't be the same size. You know how I know it can't be the same size? If it was the same size, vertically, forces wouldn't be balanced because, look, we've got an extra push down. The normal force, Dan, in this situation is going to have to cancel out both gravity and this extra push down. The normal force has to be bigger. Is that all right? See that argument? What if instead of sitting on it, what if Gershine came along and actually lifted up a little bit as Ange was pushing it? What would happen to the normal force? Be smaller. Okay? Okay. What happens to the force of friction in this situation? Well, what was our equation for friction? Friction equals what times what? Mu times the normal force. What force just got bigger? Normal force. So what other force got bigger? Friction is now bigger than Ange's applied force. They are no longer in balance. You okay with that? All right, let's answer the questions. So part A says, what happens to the weight? Did the mass of the bench itself change? So did gravity change? No change. B says, what happened to the normal force? Oh, what happened to the normal force? That's the force in this free body diagram that changed. The normal force increased. That's how I'll write that. You can write the normal force increased if you want, but you know I tend to abbreviate. What happened to the force of friction then? Well, if the normal force got bigger and friction is mu times the normal force, what happened to the force of friction? Got bigger. Because the normal force got bigger. So how will this block bench move? Well, looking at my new free body diagram, the one on the right, which way must it accelerate? Look at it. Which way must it accelerate? To the left? Which way was it moving? So if you're moving to the right, but you're accelerating to the left, how does that manifest in the real world? What will we see the block doing? Slowing down and come to a stop. Slows down. We're just looking at the split second right after Gershine sat on the bench. We're not going to, because I know it would come to a stop pretty quick. And then that's a different situation now. Is that all right? Yeah. It says, explain your answer using principles of physics. I think we did with our good free body diagram and walking through all of that. I'm going to get a little bit technical on you because it's nerd trivia. I'm not going to test you on this next little bit, but how many of you actually ever slid something really heavy across the floor? Like furniture or whatever? Not many of you, a couple of you. Okay. You may have noticed it's something, next time you're sliding something, try and notice this. Getting it moving, you have to push harder than to keep it moving. Once you have it moving, once you have it sliding, you can actually ease up a little bit. Have you noticed that? That's because actually there's two different types of stickiness. I'm not going to test you on this next bit, Dan. We're going to pretend for the unit that there's only one type of stickiness. We're going to use it interchangeably in any situation. But to explain why you can ease up, I'm going to tell you there's actually two different types of stickiness. There's friction on an object when it's at rest because those hills and valleys will lock up. Those microscopic hills and valleys that we talked about between two surfaces, they'll lock up even when we apply a small force to an object. When the object is at rest, we call that static friction. Static friction means not moving or not changing. Static means not moving or not changing. So we're going to do a little thought puzzle here. It says this: suppose we pull on a desk with a force of 2 newtons and the desk does not move, then which of the following is true? So I'm going to walk over to Mud's desk here. I'm pulling with about 2 newtons-ish. Is the desk moving? Okay. Which of the following is true? A, static friction is greater than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there's no static friction at all. Once again, guess what? We're going to vote. How high you hold your hand up is how sure you are of the answer. So there's our situation. I pulled on Mud's desk with 2 newtons. It did not move. Which of the following statements is true? Who says, Mr. Duick, obviously static friction is bigger than 2 newtons? 1, 2, 3, 4, 5, 6, 7. Ange, was that a vote up or not? 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Who says static friction is exactly 2 newtons? Who says static friction is less than 2 newtons? Who says there's no friction at all? Someone didn't vote. They know who they are. I know who they are. Next time I'll make sure they vote. You know what this might be a good job for? Let's do a side view of the desk. So sitting where Dan is, what Dan would have seen when Mr. Duick was tugging on the desk. Here's the desk. Mr. Duick, first of all, what are the forces acting on this desk at the audience? One? Okay. What else? And I think same size. How hard was Mr. Duick pulling? Exactly how big? You know what? We'll call that F applied. I got rid of the underline because it looked like it was part of my arrow and it was creeping me out. Sorry. What else? Friction, which way? Bigger, smaller, or the same size? So if it was bigger, don't write this down, which way would the desk have to be accelerating? Did the desk accelerate backwards? So I ask you again, bigger, smaller, or the same size? What's the correct answer? Has to be. And it says explain your answer using, and I kind of used Newton's first again because it wasn't accelerating. The forces must be, I'm looking for the special letter be balanced. Is that all right? By the way, if it was bigger, what that would mean is as soon as I let go, the desk would have knocked my back, it would have gone shooting that way. If it was less, oh, by the way, this is how sliding something works. Let's suppose we calculated that the biggest friction can possibly be is 10 newtons. How big? How big? If I pull with 5, how big is friction? 5. You know how I know? We're not accelerating. What if I pull with 6.3? How big is friction pulling in the opposite direction? What if I pull with 9.8? But as soon as I pull with 10.4, oh, there it was. By the way, I could feel through my hand that it was getting ready to go. You can kind of tell. As soon as I pull with more than friction can match, as soon as I pull with more than static friction can match, now I'll accelerate in an unbalanced direction. So, next page over, static friction acts when you have two objects that are at rest relative to each other. As an example, static friction is what keeps a car with its parking brakes from sliding down the hill. A block of wood will remain stationary on a sloped table because of static friction, at least for a while, as long as it doesn't get too steep. Static friction is what keeps you standing still on a roof if you're standing on a roof because you're not moving. Okay? The force required to overcome static friction is always a little bit bigger than the force needed to overcome sliding friction. In other words, Lena, once you get something sliding, you can ease up a tiny bit. Don't have to push as hard. The fancy word for sliding friction is called kinetic friction. I'm talking about this. It's going to be, I think there's a question or two in your homework, but I will not test you on this. But this is just because a few years ago, a kid asked me that question, and I thought, yeah, why don't we explain why you don't have to push as hard once you get something moving as it is to get it moving in the first place. So if we really wanted to be accurate, we would say something like this. A 5 kilogram object sits on a surface, but there's 2 mu's. When it's at rest, mu is 0.3, mu static. I used mu s. Once it starts to move, the slipperiness, the coefficient of friction, mu kinetic, is 0.25. A says, determine the force required to start the object moving in the first place. B says, okay, you know what? I think this is a job for her. I'm going to do my free body diagram, I think, right here. So here's the object. What are the forces acting on this object? Get the obvious one. Which way? What else? Normal force, let's go systematically. Bigger, smaller, or the same size as mg? Bigger, smaller, or the same size as mg? Sorry? I don't see any other vertical forces. By the way, you want to know when it won't be the same size? Something like this. See the extra vertical force in the picture? Or something like this. See the extra vertical force in the picture? Or something like this. See the extra vertical force in the picture? Or in your homework, you'll see something like that. Okay? So back to my question. Bigger, smaller, or the same size? What do we all say? Same size. Good. In part B and part C, we're going to pull on this. So I'm going to say that there is an F applied. It's going to change from question to question. Does this question want us to include friction? How do you know? It gave us some coefficients of friction. Which way will I point friction? Okay? Bigger, smaller, or the same size? Well, you know what? Since F applied is changing, I'm not going to be too fussy on my arrow length. Here's what I know. Friction is pointing that way. So I haven't quite worried about scale, but I got the directions correct, Ashley. You okay with that? Ashley, what does A want me to find? It wants me to find this F applied to get this just to start moving. Here's what I think I'm going to argue. For me to get this just to start moving, F applied has to be bigger than friction. You okay with that argument? So what I'm actually going to say is this. I'm going to say that F applied equals friction, and then I'll say as long as I pull harder than that, it'll move. There's my argument for part A. How hard do I need to pull to get this object to move? Harder than this. Friction is what times what? So I can say that F applied is mu times the normal force. Which mu? Zach, are we sliding yet, or are we still at rest?
Rest.
So am I going to use the kinetic moving friction mu or the still at rest static mu? In fact, if you want to, you can put a little S underneath your mu. Good, you're writing stuff down again? Excellent. You were zoned out for a second there. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force has to be the same size as the normal force? Okay. Did they give me M? Yeah. Did they give me G? Yeah. Let's just go straight to our calculator. It's going to be 0.3 times 5 times 9.8. You have to pull harder than this to get it to move. Sorry? What'd you get? No, no one? Okay, I'll beat you to it. And I'm going to carry all my sig figs because I'm going to use this as a comparison for other stuff. So 0.3 times 5 times 9.8. 14.7? Okay, so really I would need to pull with 14.71 and now it will accelerate. But that's the cutoff. How hard do I need to pull to get this to start to accelerate? Harder than that. What if I pull with 5 newtons? Will it accelerate? What if I pull with 6 newtons? Will it accelerate? Oh, let's look at part B. Lena, in part B, how hard am I pulling? In part B, how hard are we pulling? Is it going to accelerate? Nope. So what's A exactly as a number? I can say without even thinking about it, A is 0. Not only that, I can tell you how big friction is. Friction, if I pull with 10, is not 14.7. Friction, if I pull with 10 and it doesn't accelerate, how big must friction be in the opposite direction exactly? Got to be 10. What if I pull with 12? Will it accelerate? How big is friction? 12. What if I pull with 13? Will it accelerate? How big is friction? 13. What if I pull with 14.6? Will it accelerate? How big is friction? 14.6. And if you were right around 14.6, 14.7, you would be able to feel through your hands that this object was ready to move. We've moved enough things, we can kind of tell that. Okay. Ooh. How hard are we pulling in part C, Callie? So will it accelerate now? Okay. Completely different situation. Who's winning? Who's losing? Equals MA. So my equation now is going to be that. Okay. It wants me to find the force of friction. I'm going to do that right over here. Friction is what times what? Now, here's the key difference. Are we sliding now? Yeah? I'm going to use the kinetic mu, the 0.25. It's going to be 0.25 mg. So friction when it was standing still was 14.7. How big is it once we get it moving? Could you crunch that, please? Jan, what'd you get? 12.25? This is why it's a little easier to keep something moving once you get it moving. You don't have to push as hard. Friction got a little bit smaller. So if I walk that over here, first of all, how would I get the A by itself? Because they want me to find the acceleration. How would I get the A by itself? I'll get the acceleration is F applied 20 minus 12.25 divided by 5. Which is what? I might be able to do that one in my head. 20 taken by 12 is 8, taken by 0.25 is 7.75, divided by 5. What's an easy way to divide by 5? Divide by 10 and then double it. So it'll be 0.775, double it. So it'll be 1.4. It'll be 1.5. No, what do you get? 1.55? I should have been able to get that. Units, it's an acceleration. Okay? So in your homework, there's going to be kind of a clone of this question where I give you a static coefficient of friction and I give you a kinetic coefficient of friction. I will not do that on the test. I will just give you one and you can use it in any situation. So I wrote here, to keep the math nice, I'm going to treat both types of friction as the same thing. So friction is just going to be mu times the normal force. Oh, we got a visitor. Where mu is the coefficient of friction, that's what we call it. And we're going to get the normal force from a free, wait a minute, what's a good abbrev for free body diagram? We're going to get that from an FBD. Okay? Example 4 says, find the maximum force of friction. If we did pull on this object, how hard would we need to pull to get it to move in the first place? For each of the following, and I wrote here, technically this is mu static and this is static friction, but we're going to pretend they're one and the same thing. I'm going to zoom in on this first one. I'm just going to do a vertical free body diagram. I'm going to do the vertical forces. What are the forces acting on this 8? Get the obvious one. What else? Bigger, smaller, or the same size as mg? For this question, friction, technically static friction, but I'm not going to be that fussy, is mu times the normal force. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. What? So here, I could say mu mg. And if I wanted to calculate this, hey, what's mu? I don't know. What's mu with you? 0.35? Yes? Times 8 times 9.8. What do you get? 25.2? Is that right? That seems wrong. Is that right? That seems way off to me. 27.44. I was just looking at this going, I think there's going to be at least 2 decimals is all I was doing. 27.44? Okay. Now, in part B, what's weird? What do you notice about part B? There's an extra vertical force. See it? So here's what I can tell you right now. The normal force is not going to be mg. But we're going to start out the same way. This is the job for a free body diagram. What are the forces acting on this? Get the obvious one. Okay. Is this sinking into the ground like quicksand? Is it flying through like Superman? So vertically the forces are balanced. So there has to be a normal force, but it's not mg. Is it going to be bigger or smaller than mg? In fact, it's having to cancel out both of those. I'll exaggerate it so it catches my eye. Okay. Taryn, what did this question want me to find? The maximum force of? Okay. Friction is mu times the normal force. Taryn, what's mu? I don't know what's mu with you. What's mu? Okay. But you know what? I don't know the normal force. And it's not mg. I can't go, oh, but look. I need to do a little bit of thinking, and I'm going to do that thinking off in the margin right here. I'm going to say, are we sinking into the ground like quicksand? Are we flying it like Superman? That means as an equation, everything up has to equal everything. What's everything up? There's only one arrow. Which arrow's pointing up? The normal force has to equal what's everything down. There are 2 arrows. And when you say and, I think you mean plus. Yes? That's the normal force. It's whatever that, oh, you know what? I'm lazy. Look up. Mu times, in brackets, the normal force. That's the expression for friction in this situation. It's going to be bigger because someone's pushing down on this object. What do you get? This is also my way of saying worth trying on your calculator to make sure you're comfy with brackets and stuff. I'll fill in the numbers. We probably should fill in the numbers for our notes. In your homework, if you go straight to your calculator from this line, I'm fine. Here in our notes, just so you know, I'm thinking I went 0.35 times 8 times 9.8 plus 55, close bracket. What do you get? 46.7 even, or give me all the sig figs. I get 4 sig figs, isn't it? 46.69 newtons. Is that right? Yeah. Look at diagram C. Do you think friction is going to be bigger or smaller in diagram C? Why? So which force is that actually affecting? Why is friction smaller? Because the normal force is going to be smaller. Why is the normal force going to be smaller? It's not having to cancel out all of gravity. Okay, this is a job for a. This is a job for a. It's a little call and response here. I'm trying to build certain circuits in your brain so that when you ask yourself a mental question, your brain answers yourself, right? Right? You good? Okay. Dan, what are the forces acting on this? Get the obvious one. I agree. Are we sinking into the ground like quicksand? Are we flying like Superman? So there is a normal force, bigger, smaller, or the same size as mg, Dan, my friend. Why can't it possibly be the same? Is there an extra vertical force? Can't be the same. So that's what I'm going to say to you. If you see an extra vertical force in the picture, run away. It's not the same. We got to think about this. Someone's pulling up with 55 newtons. What's that going to do to how hard the ground has to push to cancel out gravity? Is the ground going to have to push harder or less hard? Normal force is smaller. Dan, I'm going to exaggerate it, bloop, so it catches my eye, so that I notice normal force is smaller. Okay. Dan, what did this question actually want me to find at the very beginning? It said find the... Okay, friction is what times what? So I would still start out going mu times the normal force. Dan, hey, what's mu? I don't know, what mu? 0.35, yeah. I don't know the normal force, and it's not mg. This is by far the biggest mistake kids make. They start thinking, well, was mg all the other? No, that was because we were doing boring questions. Are we sinking into the ground, Dan? Sure, no. Are we flying into the air? What that means is vertically, everything must be, I'm looking for where that starts with letter B. As an equation, that means everything up has to equal everything. How many arrows are pointing up? Can we see two? Okay. How many arrows are pointing up? So my equation is going to look like this. Everything up, normal and 55, has to equal, what's everything down, Dan, my friend? Just read me the arrow that we labeled down. That's it. I want to get the normal force by itself, because that's what I need way over here. How would I get the normal force by itself? Subtract 55? Yeah? Is that okay? Do you want to, you know what? Let's be lazy, Dan. Is that okay? So, for this third situation, it's going to be mu bracket mg minus 55. And I'm not going to memorize which one's plus, which one's minus. I'll derive it each time from a good free body diagram, Brea. I think that's better. Some kids are like, oh, okay, I'll memorize. If the arrow is up, I subtract. I hope you can kind of do it intuitively from the diagram. I hope. I think that's better. Let's plug in our numbers. What's mu? 0.35 bracket 8 times 9.8 take away 55, which is what? Can you give it to me to three, like all the decimals? 8.19? Okay. I guarantee in your future, I like this question, I'll give you a question where the normal force is not mg. So Dan, there will be an arrow pointing up, an extra arrow, or an arrow pointing, and you'll need to spot it. You see what I mean by those arrows? Yes. And you'll need to realize, okay, in this question, normal force is not mg. I'll have to think everything down has to equal everything, or everything up has to equal everything. Same diff. And again, really, we used Newton's first for that. We knew it wasn't accelerating vertically. By the way, so what does that mean? To get object A accelerating to the right, you would need to pull with more than how many newtons? 27.44? To get object B accelerating to the right, you would need to pull with more than how many newtons? 46.69. To get object C accelerating to the right, you would need to pull with more than how many newtons? Otherwise, they're not going anywhere. Okay. Example 5 says this. For each of the blocks below, A, write a vertical force equation. B, find the force of friction. C, write a horizontal force equation. And D, find the acceleration. You know what? Let's kind of do these simultaneously. I'm going to draw, whoop, I did that the wrong way, Mr. Dewick. I'm just going to draw a line down the middle of the page, kind of like that. Jan, what does part A want me to do? Anybody have a suggestion for what I should probably do first? I think I'm going to do a free body. So Jan, let's you and I do the free body diagram. On the left. Oh, did they give me a picture, Jan? Then I'm not going to do a dot. I'm going to be lazy and label the picture. So here on the left, what are the forces acting on this? Get the obvious one. What else? Bigger, smaller, or the same size as mg? Yep. No extra vertical forces. What else? I see that 20. See it? What name did we give to the mystery force that was coming from off the page? Do you remember? Yep. Does this question want me to include friction? Psst. Does this question want me to include friction? Does this question want me to include friction? Yes. How do I know? There, boy. I was running out of ink here. Digital ink. Okay. Which way is friction going to be pointing? Bigger, smaller, or the same? I'm going to assume it's smaller than F applied, but I'll find out. Okay, there's my free body diagram on the left. Jan, the right-hand one is going to be a little bit trickier. How can I tell at a glance that the right-hand one is going to be a little bit trickier? Extra vertical force. Okay. Anyways, get the obvious one. That hasn't changed. What else? What do we usually do after gravity? Bigger, smaller, or the same size as mg? What do you think? Bigger. I'll exaggerate it so it catches my eye. Good. What's that 20? And friction. Cool. Good job. Manveer, what does part A want me? Now that we've done the free body diagram, what does part A want me to do? Write a vertical force. Read part A. Write a vertical force equation. Okay. By the way, I can tell you what the vertical force is. It's 0. How do I know the net force vertically is 0? We're not accelerating up or down. So I'm not going to ask you to find the net vertical force. The equation. Okay. What that means is everything down has to equal everything. In part A, my friend, what's everything down? Only one arrow. mg. Has to equal what's everything up? Good. And we're done. On the right-hand side, everything down has to equal everything up. What's everything down? Careful. There's a number right next to it. Why don't you just read the number? Gravity and the... I don't know, but there's a number right next to it. Just read the number. Gravity and the 15. And the... Everything down. Yes? Has to equal. What's everything up? Yep. And you can see, yeah, the normal force is bigger because normally it's mg. We're adding to it. Bigger normal force. Which, by the way, I guess means more friction. Because friction is mu times the normal force. Okay, cool. Raj, what does B want me to find? Friction is what times what? Let's write that down. Raj, what's mu? I don't know. What's mu with you? What's mu? I don't know the normal force. Oh, but look. I know the force the same size as a normal force. In fact, you know what? I can even get it right from here. What can I replace the normal force with? Let's plug in our numbers. So this is going to be 0.12 times 10 times 9.8. I can do this in my head. 10 times 9.8 is 98.12. It's going to be 9.8 plus 1.96. 10.8. 11.76. Double check me. 4 sig figs in my head. Just saying. Units. It's a force. Okay. Let's keep going. Let's do the right-hand one. What does B still want me to find? What is friction still? Mu times the normal force, which is going to be 0.12. I don't know. Wait a minute. What can I replace the normal force with here? In brackets, mg plus 50. Why in brackets? Because that whole thing is the normal force, so that whole thing needs to get multiplied by the 0.12. Do this one in your head, Mr. Dewick? Well, maybe. It's going to be 10 times 9.8 plus... Sure, I can. Yeah, 10 times 9.8 is going to be 98 plus 15 is going to be 113. 0.12 times 113 is going to be 11.3 plus 2.26. 11.3, 13.56? Yeah, okay. Cool. Well done. Brea, what does part C want me to do? What I'm really, who's winning? So let's look at this first situation. Who's winning? I think F applied. Who's losing? What does winner minus loser always equal? What about on the right-hand side, Brea? Who's winning? Who's losing? Equals? Oh, same equation? Really? Wow. Does that mean we're going to get the same answer for both of these? No, why? Because friction, we've mucked around with friction. Okay, but it's the same tug of war. The applied force and friction are battling it out. Ashley, what does D want me to find? How will I get the A by itself? A is going to be F applied minus friction divided by M. It's going to be, what was F applied, 20? Minus, I know friction, 11.76 divided by, oh, I can do this in my head. I can divide by 10 in my head. It's going to be 20, take away 11 is 9, take away 0.76 is 8.23. 0.823? No, 0.824, because there's a 6. Dewick. Oh, I was on such a roll. And dividing by 10 is where I made a mistake. 0.824? Units, Ashley? So it's moving. Not very fast, but it's moving. It's accelerating, but just barely. Oh, you know what? Same equation, isn't it? F applied minus friction all over M. Yeah? F applied was still 20, but now friction was 13.56 divided by 10. Make up for it, Mr. Dewick. Get this one right carefully. 20 take away 13 is 7. Take away 0.5 is 6.5. 6.44. 0.644. And I carried the one correctly this time, didn't I? Wow. By the way, what if the applied force wasn't 20? What if it was 12? What would happen? Two possibilities. If we were at rest, we wouldn't move at all because static friction would match the 12 and just cancel it out. If we were already moving, we'd be slowing down. I don't know which one. I don't have enough information. Again, Newton's laws don't tell us anything about motion. They tell us acceleration. This is just to give you an idea of what's big or what's small. You do not need to memorize this. I will not quiz you on this. But to give you an idea of some mu's, some coefficients of friction, wood on wood is about 0.25. Steel on steel, there's actually a fair bit of friction. How do we get around that in machinery where we have steel on steel all the time? Yep. When you lubricate it, it goes down to about 0.1. Still some heat going to be generated and still some wear and tear, but much better. But this is those that have cars or vehicles. There. That's why we put oil in there. Otherwise, they would not last very long. Rubber on dry asphalt. This number, this depends on a lot. In the summer, on a hot day when the pavement feels sticky, if you have good tires that have also been sitting in the sun, this can be as high as about 0.75. In the winter, when it's colder, drops to about 0.4. But here's what I want you to notice. When it rains, your mu goes down by about 50%. And so I'm talking to all of you as, because you know I love you, but I got to be honest, stupid young drivers. When it rains, slow down. I always have some person, usually a guy, I'm a good driver, I can handle it. It's nothing to do with you. The physics says you have half the stopping power that you're used to. Slow down. Figure it out. It's not your skill. You can't argue with the universe. Rubber on ice, really slippery. That's why rubber shoes on ice don't work very well. Steel on ice, you get a little bit of grip. These are very approximate. Can you have a coefficient of friction bigger than 1? Rubber on glass has a mu of about 0.2. That's why a thin piece of rubber, you can stick it to the glass, walk away, and it'll stick there because it can support its own weight and then some. A dragster tire has a mu of 2.8. Dragster tires are very sticky. Shouldn't a tire with so much friction slow the dragster down? Shouldn't the tires be sticking to the road and slowing it down? Using principles of physics, explain why a high coefficient of friction is essential for dragsters. What does it say is the hint, Mud? Well, let's draw a free body diagram. Here's my dragster. What are the forces acting on it? Get the obvious one. Which way? Okay. What else? Zach, is the dragster sinking into the ground like quicksand? Flying like Superman? So? Yep. You with me? Because you're looking zoned out, my friend. Okay. What else? Well, first of all, let's suppose we're at the starting line and we just stepped on the gas. Which way is the dragster going to accelerate? Which way had there better be an unbalanced arrow? Which way is the dragster going to accelerate? Forward to the right. Which way has there better be an unbalanced arrow? Forward to the right. Left? It's got to be an arrow pointing this way. Otherwise, the dragster is not going to accelerate forward. What force is that? What? There is no applied force. Common mistake. Also among physics teachers. This is where I had to correct a physics teacher a few years ago. What force makes a dragster go forwards? Friction. That's what's, and there's no force pointing back. There's a tiny bit of air resistance, but our dragster is pretty aerodynamic. There's a reason they all look alike, okay? So yeah, that's the basic free body diagram for a dragster when you step on the gas. Which force makes the dragster go forwards? Not applied. Which force, Danica? So the bigger friction is what? More acceleration. In fact, if you watch dragsters, they do a smoke show just before the starting line. That's not to impress the crowd. What's stickier, hot rubber or cold rubber? They're trying to get their tires even a bit more melty. They're trying to increase the mu, because what force is it that pushes a dragster forwards? Friction. This is the free body diagram for a car moving forwards. In lesson 5, in the last unit, there was a dragster question. I'm giving you a big hint. That's your free body diagram for that. Is that okay? Trying to see how much more I'm going to get. So here's what I'm going to do. I'm going to pause here. We're going to watch a short video though. So I've taught you that your bodies are backwards accelerometers. I've said that when you hit the brakes, you're slowing down, you're accelerating backwards, but which way does your body feel like it's getting pushed? Forwards. When you step on the gas, you're clearly accelerating forwards, but which way does your body feel like it's getting pushed? Okay? There is an object, however, that if you put it inside your car, it will point in the direction of the acceleration. When you step on the gas, it will point forwards. When you step on the brakes, it will point backwards. What object is that, you ask? What object is that, you ask? What object is that, you ask? So glad you asked. Put your pencils down, look up. Works better if my video player opens right away instead of having a long delay. This is a really long delay. What's going on here? There we go.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So today we're in the rocket van, and I've got two little science helpers here, right? Wearing your seatbelts? Okay, we're going to do something pretty interesting. Check this out. I've got a pendulum suspended from the top of our family van, and we're just going to drive forward. We're going to accelerate. So if we're going that way, which direction do you think this pendulum should go?
Okay, first question. If we're moving that way, to the right, and we step on the gas, which way will this string end up moving? Will the pendulum swing back, or will the pendulum swing forwards? Let's find out.
3, 2, 1, go.
So the pendulum also behaves like our bodies. It's an accelerometer, but it's a backwards accelerometer, because we're clearly accelerating forwards, yes? But which way did the pendulum move? Okay.
Which way is it going?
My way.
That's right, because I'm accelerating, right? Does that make sense to you guys?
Yes, sir.
Okay, very good. I was hoping it would make sense. So we're going to change it up just a little bit. Okay, so now what I'm going to do is I'm going to replace this pendulum with a balloon. We should see the same thing, right? Let me cut this off. So what we're going to do is we're going to accelerate that way, so we have the mass of the balloon and the acceleration, so that should then a force and we'll have to react with the string, right? You guys ready?
Yes, sir.
3, 2, 1, go. Wait a second.
Which way are we accelerating? Which way is the balloon pointing? Why?
What just happened? Oh,
And also, now he's slowing down. Which way is the balloon pointing? Why? You can try this as long as you're not the driver. If you do ever have a helium balloon, like you pick one up for a party, take a second, go out into the parking lot somewhere, and you can try this, and you'll see this absolutely works in your car. By the way, also, if you go around a corner, it will point inwards towards the center of the corner, because that's which way you're accelerating. When you're going in a circle, you're actually accelerating inwards, not outwards. This will work. Do you have a suggestion as to why? Read what? Okay, so first of all, balloons don't float. What they actually do is they move to less dense air. Less dense air up, they'll move up. When you step on the gas, air has mass. Air actually sloshes to the back of the van. The back of the van is slightly more dense than the front of the van. And so the balloon will move to the less dense air at the front. When you hit the brakes, the air actually sloshes to not enough that you can notice, but the balloon certainly can tell.
It goes backwards when I stop. What's happening?
It's still the same.
3, 2, 1, go. There it is, coming right at me. Why is it doing that? Do you want to know?
Yeah.
I brought something to show you. You remember I told you I was going to bring this jar earlier? Remember that? So it's like this. Imagine this entire van is just like this jar. And all the air inside this van is just like the water in the jar. Does that make sense? So let's imagine that the balloon is this bubble on top. Because the helium in the balloon is lighter than air, right? So that causes it to do what? Go up, that's right. So if I've got this air that's just like it, what happens if I move the jar that way? All that water sloshes to the back. And when that water sloshes back this way, which direction does the bubble go? You see that? So the air bubble moves in the direction of acceleration. Does that make sense? I know you're 5, but I think you can do this. Okay, so I've got my seatbelt on. If I drive forward real fast right now, which direction is the balloon going to go?
That's a good question. So if we drive forward, which direction will the balloon point?
Forward.
Why will it go forward?
Because of all the air splashing back.
That's right. Very good. Watch this. Look at that. You see that? So you know what that means, don't you?
Also, you see he's doing a corner, and it's pointing towards the center of the corner. It's pointing inwards. Okay. You can make your own little accelerometer if you want. Let me pause the video.